be identified by the which can be known from the eigenvalues of AX or the leading exponents, then using this approach we can compute the Katz invariant, as it is shown in this example. So this is a matrix AX, and this is a associated valuation matrix of AX. I just put the pole on the same side. And here M has only one eigenvalue, which is 5/3. So M is the tropicalization of A of X. And so the Katz invariant is 5/3. The exponential parts will be given as such. However, in this, as I said, that in this approach, there are singular cases left. And what we noticed that these two approaches can superpose to give us an answer or a method to compute the Katz invariant without passing through the characteristic polynomial. And this will be another application for Moser's criteria and algorithm. So if you go back to general singular case, we can see that this is not a singular case for the tropical algebra. And it's not just an observation, it can be shown why. And so we are still investigating this question. And another question we are investigating that since we can treat the turning points of perturbed systems, then maybe the same approach can be borrowed or can work for a matrix with two parameters to find its eigenvalues and eigenvectors. So this is these are the applications of the Moser-based algorithm. I thank you for your attention, and here are some references.
More questions?
You mentioned something about interpolated conditions in the bivariate case.
About
the bivariate case.
Yes.
Could you elaborate a little bit on this?
About the bivariate
integrability conditions.
Integrability conditions. Yes. Well, in fact, the integrability conditions for this system, I'll just show it so that I can write the integrability conditions. So here's the system, and we know that in the language of operators, the operators compute, and we can show by some computation that the integrability condition delta 1, delta 2 equal delta 2, delta 1 can be rewritten as x p plus 1 del b by del x plus ba is equal to ab plus y q plus 1 del a by del y. And so our main concern was to see if the terms which will be multiplied by x minus 1 upon applying the shifting or the shearing in B are already zero or not, because if they are not already zero, then this will introduce poles in B. So we were using we tried to look closer into this integrability condition to see what do we have for bx equal to 0 y. And so for this, if we set x equal to 0 in this integrability condition, we will get dA, or I'll write it this way, bx equal to 0, a0 now. Everything is in y, so a0 is the leading term in the first system. a0, y, b. Equals 0 y plus yq plus 1 del a0 y del y. And so by considering this relation between a0 and b, we can see that in this case bx equals 0 y, or A0y lie in the eigenring of Bx equal to 0y. And the eigenring is the ring of all the matrices T. So the eigenring of B is the set of all matrices T such that delta T equals TB minus BT. And in an article for Barcato in the 2004, it is shown that if an element in the eigenring has a triangular form or a certain form, then B itself will have a certain form. So if we, here in this case, we have A0 in the eigenrange. So if we write A0 in this Gaussian form, then Bx equals 0 will have a 0 here. So here we can multiply by x minus 1. And this is why we added again more structure to get a 0 here. So we can multiply here by x minus 1. And this is the way we guarantee that poles will not be created in B. Because
I'm a little surprised at your condition that you wrote down on the top. Yes. X to the p plus 1, that if I only look at your equation and forget about the x, I mean the Poincare ranks. Let's say I forget about that. I mean, that's the two equations you're given, right? The other is just another way to write it.
Yes.
Then the integrability, why would the integrability condition depend on P and Q?
Yes, you are right about this. In fact, here I factorized xp and I factorized yq. So in fact, it is inside. And this is inside. But I factorized them so that I can set x equal to 0 and work smoothly.
Okay.
You are totally right about this remark.
More questions?